All right, so let's talk about some examples that are scalable using what's called sum reduction. So here's an example of something that has strong scalability, and there's not much interdependency, right? And the book talks through this really well, right? If you have, let's see here, this isn't the exact book example the book gives, but 100,000 numbers on 100 processors, right? They have unified cache, okay? So they can all access the same cache. That's what the U and the E stands for, right? Then they'll give each processor an ID, right? Processor name 0 to 99. Okay. Very complicated so far, right? And does it talk about the goal here first? It doesn't. But the idea is you want, oh, it does. It says right there. You want to sum all 100,000 of these, right? So you just divide it out, right? This is very independent, but how can you balance the workload amongst each processor? Well, the simplified way is just give each processor 1,000 numbers to hash, right? To add up. Once you've done that, what do you have left? Once you hand each of the 100 processors 1,000 numbers to sum up of the 100,000 numbers, now what kind of result do you have?
100 different sums.
Say that again?
100 different sums.
Right, so what's called partials, right? Because that's not all of them all added together yet, right? So the idea is then, after that, what you do is you do sum reduction. So you add up each of the partials with a different CPU adding up partials, and then another CPU is adding up those partials, and there's another CPU adding up until you get to the final partials all being summed together, okay? But this is a highly simplified example, but it just is to show you the tip of the iceberg when you start dealing with hundreds of processors and trying to find a way to balance them for the workload at a software or an algorithmic level solution. That's why sometimes having hardware solve the problem could be nicer at like a fine-grained level, at SMT level, right? Any questions on this? Has anyone, so somebody said they had done a little parallel processing. Who said, did you say you had done some? Which language did you use?
Java and C# both.
Oh, wow. Okay, so you didn't use a native parallel processing language? Was it a cluster or?
It was doing clustering with servers over using Java.
Okay.
And then C# for the management part.
Oh, okay. Interesting. Interesting. So there are some languages, we'll talk about it later, that people have put out there to try to, as a management language, help you think about some of the challenges when you're programming in a parallel environment. Okay. Which language did you use?
Python.
Okay. Interesting. Very interesting. Now, did you guys, Python has threading, right? So that might be why, and Java obviously has threading.
Mm-hmm.
So maybe that's why. Was there a lot of threads?
It would do up to 8.
8 threads?
Mm-hmm.
Okay. So that might be why you guys chose to do that. Okay. So even in this example though, synchronization is still necessary. That's why that's a good starter example too, right? It's because even after they've added up all the partials, they still need to communicate, right? So it would be a bad thing, right? If processor C has, I've got to give them a name, partial 1, partial 2, partial 3, partial 4, right? Processor B has none and processor C is waiting, right? So if processor B is not finished, now we get data race conditions again, right? Summing up these partials, and processor C grabs this, and maybe it grabs 3 and 4 from another, right? Processor D, right? Now it's just going to grab whatever B gives it, even if it's not done yet, and C is going to get an incorrect result. So it's a data race condition. So you get similar problems as at the hardware level when you scale up to multiple processors. Okay, so you still need to synchronize, which slows it down. All right, let's talk about GPUs. So what does GPU stand for?
Graphical Processing Unit.
Yeah. How many people? I'm curious. How many people? Well, I mean that's not nice to say you don't have a GPU. GPUs are pretty common today, right? A lot of people game, right? So the book does a good job talking about the GPUs and CPUs came from 2 different families. Okay. So GPUs mostly came from the idea of processing graphics, okay, or sound and graphics, okay. And so because of that, in different industry standards, they use different terms. So it's very hard to get like a apples comparison between CPUs and GPUs. Okay. What is one of the major differences between GPUs and CPUs that you can think of?
Not entirely sure, honestly.
Okay. Anyone want to take a stab at it? Yes, it's on the screen. But from experience? Okay, why do you think we use GPUs for games?
Number crunch a lot faster.
Yeah, why? What number crunch a lot faster? What?
They have a lot more cores on them.
Yeah, they have a lot more cores on them, right? So, like you mentioned earlier, right, and when you're doing game design, right, you're thinking in all directions at once, right? So GPU, right, in vector style, right, what it will do is send a whole bunch of commands all on multiple data, right, at the same time, and they'll all run through simultaneously, 32 lanes, maybe 64 lanes, 8 to 64 byte words to each of those, right? What's that?
That's a giant highway.
It is. It is a very big highway. So guess what they do sometimes? Because now that highway becomes a problem. How do you keep feeding that? Why the highway can keep full? What's that? They used to fly, not anymore. That's flying is going to make it worse. We're trying to fill the lanes. We're trying to get more traffic on the bus, right? So GPUs have more cores. And now you have to feed that bus, right? When you're dealing with, as we were, like a few cores and a few lanes on most processors, right? We can hide our latency, right? If we have any latencies, because our bus isn't very wide, so we're not always trying to put stuff, right, into those lanes from memory, right? But now, if you have a ton of lanes and a ton of cores, now the issue becomes filling all of those all the time, right? So they have much higher level and more complex levels of scheduling to cover up the latency by finding multiple threads that can run. So similar to the SMT example we showed, GPUs do like an SMT to the next level. Like they want to make sure that they're filling those lanes all the time. One of the ways they fill those lanes all the time, the most common, is they're doing the same operation but on different pieces of data. So for example, when you're calculating an array, right, vectors for graphics for three-dimensional rendering, right? You can put in all 32 of those lanes, the same operation, right, for every one of those ALUs. This is going to be a sad drawing of ALUs, but anyways, for every one of these ALUs, okay, you can put in the same instruction, add, but now you have multiple data. So this is for I'm not going to go over graphics rendering in this class. So for some 3D shape you're trying to render, you'll put in the first point, second point, third point, fourth point, but add is being obtained on all of them. And maybe you get a hand movement, barely. Okay. So that's the power of graphics processing units. Now, where do graphics processing units pay for it? Where that's a great advantage over a CPU, right? Think of how many more cores they have, and you can simultaneously fill them with the same command. What's one of the trade-offs?
They heat up a lot.
Yeah, they get really hot. Okay, that's very good, right? What else? They didn't invest in cache. So generally, they have very minimal cache, okay? And they'll have specialized RAM. The RAM will have the same bus size as the GPU to keep the GPU fed, but cache you're looking at, whereas standard CPU might have, what does somebody have right now? The examples in the class are always outdated.
I've seen some with 128 megabytes.
Okay, so 128 megabytes of cache, right? Then your comparative and competitive GPU would maybe have 12, right? So they invested all their money in cores, right? You got all that hardware and development, like you can't have both without cost. So they focused on the cores, okay? And it talks about most of what we talked about right here. Bandwidth rather than latency, talked about that. And it's more multi-threaded than a typical CPU. We talked about more processors, cores. Yeah, and they're trying to solve, bigger problems. Okay. So here's a good picture of what I tried to draw on the board. This isn't working running these slideshows in parallel. It's just showing the different lanes, right, in each of the ALUs, and these are single instruction multiple data lanes, right? So even each one of these lanes actually may be an array of 32 values, right? So I mean, you're really pushing data through. So that bandwidth is the key performance here. Here are some examples. These are outdated, like I said, versus what we have today. And they're trying to give you some more pictures on how this looks, right? So you have, these are threads, obviously. So it's going to schedule a block of threads that all have their data available and ready, right, at any instance of time to fill up every lane, right? So it'll have blocks. So like one of the key language differences between GPUs and CPUs is GPUs in their scheduling algorithm will talk a lot about thread blocks, whereas CPUs, being traditional SISD, adapted to multiple instruction, multiple data, we'll just talk about individual threads and like SMT, like we talked about in here. But GPUs, they talk about thread blocks. Okay. Any questions on what we've talked about so far? Okay, I'm not going to go over vectors again. You can watch that part 1, but here's just an example of some comparable specs between a SIMD and GPU. So standard multi-core processor versus a GPU. Anyone know what else GPUs are really good for? A parallelizable task for GPUs?
Machine.
What's that?
Machine learning.
Machinery?
Machine learning.
Oh, machine learning. Okay, do you have an example?
Yeah, like the neural network that's part of the A11 Bionic chip that Apple's created. It's basically just a GPU.
Cool, so maybe that'll be somewhat of a hybrid then, if
Yeah.
Apple put it together. So, yeah, that's not one, I didn't know about that, that's cool. That makes sense though, because our brain is much more neural networked, obviously, than single instruction, single data. Another example I was thinking of, because I'm familiar with it, is like pen testing, white hat type stuff, right? If you can categorize, if you have a password or a system that takes a set of passwords, and you can isolate it to some number of events, so it's going to need 65,000 tries every 10 minutes, right? You can easily distribute that over a GPU, right? Crack a password in minutes, right? That would on a normal CPU take months or weeks or years, right? That's not a bad thing if you're doing pen testing, because you can give someone their worst case, hey, someone can crack this passcode or this hash in 5 minutes using a modern GPU. Right? Do you know where else GPUs and CPUs are available right now? Does anyone use AWS?
Mm-hmm.
So what's I haven't asked Jacob, well, what's AWS?
It's Amazon Web Services. It's a whole bunch of stuff that you can do using their cloud servers. So it's a whole lot more processing power in your system now.
Right, so you can rent time on their stuff. So, for example, there's a lot of research papers out there. Some of the best specs for passwords and stuff that are considered secure, thanks to Amazon's web server, you can crack them with the best technology renting Amazonas for like 10 minutes. And the trade-off is worth it. You pay Amazonas $100, and now you have access to a very high-level system. And so there's all sorts of issues that are arising because of technology being available readily to people using things like AWS. Right? How do you protect them? Okay, that's enough on this. Yeah, here's where it talks about, and you guys can look at this in the book or in the slideshow on your own afterwards if you want, but it really talks through all the differences in terminology because they came from 2 different development chains. Okay, so now we kind of touched on this a little bit. So what's the next type of parallel processing that's out there? Clusters, warehouse scale machines. Okay, what's an example of this besides Amazonas? Who else does warehouse level machines? Google, right? When Google built one of its first warehouse servers, right, it was a big hush-hush. What was it, Texas, I think? Big secret. I can't remember who it was. I had friends that helped build it, but this they consider a whole nother animal because they're talking about 100 to 150,000 servers or more, and everything that goes with that, like interconnections. Okay. So this is where I'll use this to transition. Let me see what's, yeah, okay. So it talks about it there. Energy efficiency and importance, reliability, but I want to use this to transition into communication. So in the chip, in a single processor, right, this is a fictitious example, right? Let's say we've got 4 cores and they're swimming in cache. This is all cache, right? They're happy cores, and it's yes, it's shared. It's not non-uniform. It's shared. So they're all sharing cache. Okay. Now we talked about in the example we did even today, right? We had the coherence table down here, right? Right. And so we had some coherency, right? How many interconnections are needed here for them each to talk to each other? Let's work it out, right? So 1, 2, 3, right? And then what?
Connect bottom left to the top right.
Okay. What are we at? Some keeping tabs? Are they all interconnected? Let's see here. Here, there. Yep, so how many connections are there?
6.
6, okay. What happens now when you have this many cores, right? 100,000. Right? How many interconnections are there? Yeah, it's called big O being squared. It scales up exponentially. So think about it. When they're doing these warehouse level servers, warehouse level scale, using that analogy of cores, kind of thinking bigger to computers themselves, right? Think about how many interconnections you're going to need to connect to that if you wanted every one of them to have direct connection, right? What's the other alternative to having them all directly connected to each other?
Routers.
Yeah, routers, right? Thank goodness, right? But routers have a bandwidth limitation too, right? So which they've gotten significantly better, right? But then the question is, how many routers do you have? How many interconnections between your routers, right? And for those who have done network topology stuff, that's a whole other class, right? So they have to deal with stuff like this on a very large scale that we don't see with CPUs right now. There are some standardized, simplified languages out there. Map, reduce, and there's another one for regions. I can't remember. Has anyone used map reduce before? But the idea is it's a simplified protocol that's built so you can renting, if you have enough money, right, to rent one of these server warehouses for like 20 minutes, right? And you can take your algorithm and you can scale it out to become parallelizable, and it'll create a whole bunch of independent intermediate results and then aggregate those. And it'll help you to find a way to see if the problem can be made into a parallel problem, and then accomplish very quickly on all their servers. Does anyone know some other traditional warehouse level servers that are out there? There it goes. It talks about them right there. Has anyone heard about SETI before? Yeah? Okay. All right. So leverage 5 million idle PCs around the world. Okay. So the end result at the end of 2011 is 2.5 petaflops, right? Does everyone understand what flops is? Talk about in the book. Anyone? Floating? Yeah. So, and this is talking about size, but we'll get into that in a second because we got to go over rooflines today. So here's the interconnections. So here are some ways to solve these interconnections, right? A standard would be bus, right? Maybe you have a router on each one of them, and they all can talk to each other. Okay? So whatever goes on the bus, everyone sees it. All right? Maybe you use a ring, right? And they can only interconnect between each other. Okay? Here's what we were getting into, right? Fully connected and the cost that you pay as you expand upward, right? So then there's other intermediate solutions for connecting these. Does anyone have any questions on this? Okay. We don't have enough time to go over this right now. Let's go over, here are considerations for a network. Your throughput, obviously, again, your link bandwidth. You'll need to look back at bisection term, the term bisection bandwidth. I don't have time for that. Cost and power, obviously, a constant trade-off. And how much we talked about the fun with routers already. I want to get to, here we go, parallel benchmarks. So how can you tell when something is good at executing parallel code? Right? Well, you can create a set of standard benchmarks. Right? We talked about benchmarks earlier in the course. Same thing, but now the idea is for parallel CPU. How well does it perform? So here are some fairly well-known standardized tests that you can run on a system to determine how effective the throughput is operating in a truly parallelizable problem like these. So these intentionally have some parallel portions in them that can be sped up and some that are maybe not so parallel. So you can determine how well it performs. Okay? Now, how do we model this though? And this is what I wanted to get to, right? Floating point operations per second, or gigafloating point operations per second. Why floating point operations? Why would we be interested in the performance of floating point operations on a CPU? It's slowest, what else?
The biggest,
What do you mean biggest?
like they require the most bytes.
Okay. What else do they require the most of?
Time.
What's that?
And execute.
Yeah, why? Why the most time, why the most bytes? You guys remember in chapter 3 when we went over, once you start to get into floating point, it uses almost all of the ALU, right? It uses the entire thing, right? And most of your stages, right? So this is a good sample set of worst case scenario, right? Floating point operations are like worst case. And it's all ALU, almost all your stages, okay? So the idea is use these, and today we're up to gigaflops, as your standardization to really tell how well something performs. And it talks about the kernel, a whole other course with operating systems and how well the hardware and the software are built to maximize the use of the processor. But here's what I want you guys to know, is using flops, we can tell how well something performs based on flops per byte of memory accessed and, where's it? It's not here. But it's basically the performance of the memory access and performing the gigaflops themselves. Let me see if it's in the next slide. Yeah, so we can create what's called a roofline diagram. Okay? Has anyone seen a roofline diagram before? Have a look at your house. All right. Eyes are burned out, I can tell from their other classes. So.
I never understood roofs. They always went over my head.
It's always above you. All right. Let's. Do you have a question?
No,
Oh, okay. All right. We create something called arithmetic intensity, right, in a roofline plot. And arithmetic intensity, it tells it right here, is flops versus the bytes. So how many flops are being performed versus how many bytes, okay? That's what arithmetic intensity is, okay? So this is kind of a way, it's a cheap way to get 3 dimensions out of a 2-dimensional graph, okay? So that we don't have to go 3D, we keep it 2D by creating this ratio for our bottom numbers, okay? And then on the vertical, we have the attainable gigaflops per second, okay? So what happens using this input, that output, is you can see what's called your peak memory bandwidth, your stream, and how many floating point operations you can achieve on the processor of interest based on your bandwidth, how fast you feed it, and how many floating point operations it can perform, okay? Eventually, you reach what's called the roofline, which is no matter how much more data you feed it, it can't go any faster. So data's just backing up, right? It's in a buffer or it just crashes, right? And so the idea is these plots are useful because you can quickly determine your peak performance of a system by running benchmark tests across it, right? As you run benchmark tests across it, right, and you feed it, you increase the memory bandwidth incrementally, right? You'll get an easy stream and what's called the peak memory bandwidth stream here to see how it's improving, and eventually you'll hit the roofline, which is the peak performance of that specific device. That's why it's called a roofline. So no matter down here, so no matter what our intensity increases, no matter how much more data we feed it, the flops is going to stay the same. So we have peak floating point performance. That's it. Any questions on that?
Where do the dotted ones come from?
Yeah, good question. So these are two different kernels that they tested at different bandwidths, and the book talks about, I don't remember off the top of my head the specific, but it talks about what it tested this kernel at and what it tested this kernel at, right? So these are specific systems that it's testing, right? The dotted lines are how it performed, right? And they're showing that performance matches what they expected for the Roofline clock. Does that kind of answer your question?
Yeah.
If you, I don't remember off the top of my head, one I think is the Xenon, the other I can't remember what the other one is. Okay, so one of them is performing at 16 gigaflops per second, and one of them maxes out at 8. But this one is not in the roofline section, so it's questionable that it might still be able to get a better performance to increase the memory bandwidth. So maybe this one is just trapped because we can't feed the processor enough. This is also useful for comparing systems against each other, right? That both have a separate roofline. Once you've obtained that roofline, you can clearly see which system outperforms the other. So this is really nice, and it's kind of thoughtful that it's at the end of the course, right? Because this is a very quick way to compare performance in a nearly apples-to-apples environment. Okay? And this is really important for parallel processing because it's very hard. You remember we talked CPI all through the course. Well, once you get into parallel processing, it gets very interesting, determining, right, how many instructions actually executed and what was the cycle count. Because different processors will have different numbers of stages, right, and different number of lanes, right? So it becomes more complicated. How do we figure out CPI here? So these bench tests and this before representation kind of gives you another way to compare. I want to go over some of the skills examples, since you guys might see this on an exam in the future, like next week. And I want to see if there's anything else to cover here. The only thing we didn't cover here, I mentioned it as we were talking through it, is just the terminology UMA versus non-uniform. Okay, I'll mention it here just so that both videos are complete. So one, uniform memory access just means that all the processors have access to the same memory, versus non-uniform, they might have separate assigned caches. Okay, chapter 6 is kind of like the final of all of this stuff. You need to understand everything else in the course to understand parallelism in chapter 6. It needs to kind of come together because we're talking both at the core level all the way down to the hardware, and then scaling all the way up to like servers and warehouse scale servers. Okay, but the concept is the same. All right, before we go over our skills, does anyone have any questions on that? Okay, so that's about part 2. I'll keep this going so the skills will be online too. Let me pull it up real quick. Pause this. Nope. That's fine. Awesome. All right, let's get the skills going here. Oops, that's not what I wanted. So the good news for this course is we have already gone over programmable logic arrays. We put that in Appendix B. So that's done. Normally that would be introduced here. I'll release the skills to you after the class so you can kind of mess with it and practice them. But let's go over the first one. Okay, so I think we're showing the same screens on both. All right, so here's an example of what you might see. Okay, so plot the roofline graph for memory bandwidth at 32 and a max flops of 32 gigaflops. So what do you all think this is going to look like based on what we've talked about? Yes, a roof. Thank you. That was turned right back on me. Thank you very much. That came right back around. So we're going to have the increasing portion, right? That's going to be dependent on what? Bandwidth. Yep. So that part, the math for that part is pretty easy, right? So if the arithmetic intensity is 1/8 and our bandwidth is 32, what do you think this first max performance? Did you say 4? So let's check it out. How about that? Right? Oops, I gotta pull the. I know this is probably the most wild concept yet throughout the whole course, right? So everyone understand, because we're limited by arithmetic intensity 1/8 right now, we're not delivering the data fast enough to execute the max of 32. Now eventually, we will deliver it fast enough where we attain 1 times 32 is 32. But why don't we keep increasing any further here?
Because the roof is 32.
Yeah, the roof's at 32. Very good. These are pretty straightforward. Okay?
I like that.
Good way to end the course. Now, in the slideshow, did you guys see the little formula that was up briefly for rooflines? Know that formula. Do you want me to pull it back up?
Yeah.
Because, and look through these skills, because sometimes they'll give it to you the other way, right? They'll give you this roofline plot and say, what's the max bandwidth and what's the max gigaflops per second, right? Then you got to use that and some thinking, right, to back out what the max bandwidth is, okay? So let me pull that back up really briefly. Right here. Hold on one second. So here it is. And let me pull that up in this recording. Hold on. This is 43.
Gigaflops.
It says gigaflops.
Yes, it does.
Sorry, we're
Attainable gigaflops.
Oh, gigaflops. That's awesome. Maybe that's peta. Gigapeta. No, I don't know. That's obviously a typo.
That is an impressive computer right there.
Yes, there's another really funny typo too, actually. I think it was chapter 5. Instead of peak performance, it says peel performance. But anyways, so if you disregard this discrepancy there in the spelling, gigaflops per second equals, right, the peak memory bandwidth times the arithmetic intensity, right? And that's going to be at your peak performance. Any questions on anything we've covered today? Yes, sir. Sorry about that.
So the roofline diagram, is it possible that your peak memory bandwidth could be higher than your peak floating point?
I haven't thought about that. It's possible, but usually today, this is my cursory thought on that, okay? I don't have a textbook. Usually today, unless we're talking about GPUs, the problem is not feeding it data fast enough. It's enough lanes to put the data in. So I don't know if there's anything out there that, I mean, I guess that'd be kind of embarrassing actually, because that means you designed and sold a system that your performance bandwidth far outdoes your processor capability, which means people paid for nothing. You see what I'm saying?
It's either the worst marketing or the best marketing.
No, but true, right? Because what we talked, this is good kind of conclusion. We talked at the beginning of the semester, I asked you guys a question, right? Someone gives you a 4 gigahertz processor with this much RAM and this cache and a 2 gigahertz, and you guys gave me blank stares. I said, which one was better, right? Well, if you don't know how to compare apples to apples, right, you might just take the marketing. This one has the highest number first. Like, they do this with cell phones all the time. My views do not represent that of UCCS. That's on the recording. Our cell phones, right? Oh, 5G. What does that mean? I don't know, but it's the 5th generation, so it must be better than the 4th generation. I'm pretty convinced that's just a marketing technique. Each of those systems are about, as a parallel example, ironically, are about bandwidth, right? Our phones, the processor on our phones are not the issue. Our phones can process data very fast. I mean, our phone processors are nearly equivalent now to what we've been using, right, on our CPU, on our computers for a long time with desktops, right? So the processor power, right, is not the problem. And a Roofline chart for phones, right, the problem is the data, right? We've got all this processor power. Our Roofline theoretically might go up to here, but our bandwidth never reaches it. So we never reach our, that's an example of where we would never reach it.
So they can be disconnected.
Right. Well, but I'm not gonna ask you to plot. I'm not gonna mess with your, like a floating line chart and you're missing this. I'm not gonna. I don't intend to do that. If one of the questions does that, please tell me. But that would be an example, right? Our phones, we can't get the information fast enough. Right? We have great performance, but we just can't get the data fast enough, right? And the faster we get the data, right, what happens to your phone in your pocket, right? Yeah, it's like cooking. You're like, what the heck? Right? You put it on your desk, right? So, good question. To help relate this to current capabilities. Any other questions? Okay, that's the last presentation. The last question. Let me pause this.